Hi all. So we are going to look at lecture number 5 of our course EC303 Applied Electromagnetic Theory. We are looking at module number 4, basically the transmission lines. In this lecture we are going to derive the expression for input impedance. It is denoted as Z suffix in a transmission line. So in this lecture we will find out the expression for the input impedance in the transmission line. So let's start with the transmission line itself. So there is a generator which we represent as VG. The generator has some kind of an impedance for it, which we represent as RG, or let's make it ZG. So this ZG is the impedance of the generator and it is not the impedance of the transmission line. And then we have the transmission line which has the characteristic impedance Z0, and after the transmission line we have the load with impedance ZL. The voltage at the input of the transmission line we represent as V0. So this point is at Z equal to 0, and this point where the load is connected is at Z equal to L. So the length of the transmission line is L. And we say the voltage across the load is VL and the load is supplied with the current of IL. Similarly, at the input you have a current I0. So the input impedance is the impedance that is seen by the generator. So what is the impedance seen by the generator when it is connected to a transmission line and to a load? So basically, if the generator looks from here, what is the impedance, which is ZA. Okay, so you can have the impedance at any point in the transmission line, but let's start with how the generator sees the impedance, and then we will expand it to the impedance at any point in the transmission line. Okay, so as we all know, the expression for the voltage at any point Z, which is the phasor form, is V0 plus e raised to minus gamma Z plus V0 minus e raised to plus gamma Z. This we have already derived. So Z means at any point in the transmission line, at any point Z in the transmission line. The transmission line is from Z equal to 0 to Z equal to L, and at Z equal to L you have the load. So load is connected, so ZL is connected at the point Z equal to L. Z is the position, and generator, which is VG, is connected at the point Z equal to 0. Okay, although Vg has, we have shown it has some kind of an input impedance here, but we are saying that whatever the voltage it is giving out is at Z equal to 0. So we can also define V0 is the input. So I represent the input as I/P, voltage to transmission line. I0 is equal to input current to transmission line. VL is equal to load voltage, and IL is equal to load current. So we have defined all the parameters. We have also stated that the voltage expression is in the phasor form is V0 plus e raised to minus gamma Z plus V0 minus e raised to plus gamma Z. We have also derived in the previous class that the current equation can also be represented as V0 plus by Z0 e raised to minus gamma Z minus V0 minus by Z0 e raised to plus gamma Z. Okay, fine. So V0, which is the voltage at the input of transmission line, implies Vs of Z at Z equal to 0, right? Because at Z equal to 0 you have the input voltage. So when you substitute Z equal to 0 in the expression of Vs of Z, we will get the value of V0. So I can write V0 is equal to Vs of Z equal to 0, that is V0 plus e raised to minus gamma into 0 plus V0 minus e raised to plus gamma into 0. You see, e raised to 0 is 1. So this is equal to 1 and this is equal to 1. E raised to minus 0 or e raised to plus 0 is equal to 1. So my value of V0, that is voltage at the point Z equal to 0, is V0 plus plus V0 minus. So what about the current I0 at the point Z equal to 0? That is Is of Z equal to 0 is equal to I0 plus, or let me write what we have written previously itself, V0 plus by Z0 e raised to minus gamma 0 minus V0 minus by Z0 e raised to plus gamma into 0. So this is equal to V0 plus by Z0 minus V0 minus by Z0. This is the expression. Okay, so let me name this expressions. This is equation number 1, this is equation number 2. Okay, so in a similar way, let's find out the expression for voltage VL, which is the voltage at Z equal to L, that is the voltage at the load. Just like we have substituted Z equal to 0 for voltage, input voltage, we can also substitute Z equal to L for load voltage, because load is at Z equal to L. So when you have load at Z equal to L, you can just substitute Z equal to L in your expression for Vs, which will give you the voltage at Z equal to L. Okay. Previously we have substituted Z equal to 0 to get the voltage at Z equal to 0, which is the input voltage V0, and we got an expression in terms of V0 plus and V0 minus. So VL is equal to Vs at Z equal to L, that is V0 plus e raised to minus gamma L plus V0 minus e raised to plus gamma L. Similarly, IL is equal to Is at Z equal to L, that is V0 plus by Z0 e raised to minus gamma L plus, minus V0 minus by Z0 e raised to plus gamma L. Let me name this as equation number 3 and this as equation number 4. Okay. Fine. So we have expressions of V0 plus, V0 minus, VL, IL, V0, I0, etc. etc. Let's make this expression a bit more compact. So from equations 1 and 2, you have V0 is equal to V0 plus minus V0 minus, and I0 is equal to V0 plus by, this is plus, Z0 minus V0 minus by Z0, which is equal to V0 plus minus V0 minus by Z0. So I can write, you can bring this Z0 towards the left hand side. So I can bring this to the I0 side. So I can write this as Z0 I0 is equal to V0 plus minus V0 minus. So let's name this as equation number 5. So you can solve equation number 2 or 1 and 5. So this is equation number 1, which we already did. So solving equation number 1 and 5 implies you can add 1 and 5, you will get V0 plus Z0 I0 is equal to 2 V0 plus. So our main aim is to find the input impedance without V0 plus and V0 minus terms in it. We need to get the expression for input impedance purely based on the known parameters, which is the output impedance, the characteristic impedance, length of the line, and even the propagation constant. We should not have any V0 plus or V0 minus terms in them. So that's our main aim. So in the equations 1, 2, 4, 3, 4 and 5, we have V0 plus and V0 minus. We are trying to eliminate the V0 plus and V0 minus so that we can have the final expression in terms of the known parameters. Okay. So this is the expression for V0 plus. So I can write V0 plus is equal to 1 by 2 V0 plus Z0 into IC. Let's name this as equation number 6. Okay. Similarly, I can also subtract (1) and 5 to get V0 minus Z0 I0 is equal to 2 V0 minus, implies V0 minus is equal to 1 by 2 V0 minus Z0 I0. This is equation number 7. So all the current V0 plus and V0 minus we have got from equations 1 and 2, and this is for expressions for our value of V0 plus and V0 minus at Z equal to 0. Okay. So these expressions are for at Z equal to 0. So can we also find the similar expression for Z equal to L at the load? So let's write up the equations number 3 and 4. So from 3 and 4 you have VL is equal to V0 plus e raised to minus gamma L plus V0 minus e raised to plus gamma L, and IL is equal to V0 plus by Z0 e raised to minus gamma L minus V0 minus by Z0 e raised to plus gamma L, implies I can write this as V0 plus e raised to minus gamma L minus V0 minus e raised to plus gamma L by Z0. So I can bring my Z0 to this side and I can write it as Z0 IL is equal to V0 plus e raised to minus gamma L minus V0 minus e raised to plus gamma L. So this is basically our old equation number 3 and this is our new equation number 8. Again, we can solve both the equations as follows. Solving equation number 3 and 8, we can add 3 and 8. So when you add 3 and 8, you see that you have a common term of V0 plus e raised to gamma minus gamma L in both, and there's a minus term for V0 minus e raised to plus gamma L on both. So it will get cancelled. So you will have VL plus Z0 IL is equal to 2 V0 plus e raised to minus gamma L implies V0 plus is equal to 1 by 2 e raised to minus gamma L into VL plus Z0 IL. So basically I moved the 2 and e raised to minus gamma L to the left hand side. So e raised to minus gamma L or 1 by e raised to minus gamma L is equal to e raised to plus gamma L. So I can write this as V0 plus is equal to 1 by 2 VL plus Z0 IL into e raised to plus gamma L. So this is equation number 9. Also, if you subtract equation number 3 and 8, you will get VL minus Z0 IL is equal to 2 V0 minus e raised to plus gamma L. Again, I can bring 2 and e raised to plus gamma L to this side. So, we will get V0 minus is equal to 1 by 2 e raised to gamma L into VL minus Z0 IL. And e raised to 1 by e raised to gamma L is equal to e raised to minus gamma L. So, this is equal to 1 by 2 VL minus Z0 IL e raised to minus gamma L. And this is equation number 10. So, we have found the equations for V0 plus and V0 minus at the load. So, we have expressions for V0 plus and V0 minus at the generator, and we have expressions for V0 plus and V0 minus at the load. So, the Z-in that we are going to define is the input impedance at, or I can say looking from the generator at Z equal to 0. Okay. So, you can define Z-in is, so basically it is the ratio of voltage and current. So, Vs of Z equal to 0 by Is of Z equal to 0. Currently, we define Z-in as like this, but it can be at any point in the transmission line. So, currently we say you are looking at Z equal to 0 and you are finding what is impedance. You can look at Z equal to L dash at any point in the transmission line and you can still find the input impedance. So, for simplicity, we are just looking at Z equal to 0. Okay. So, from equations 1 and 2, so basically the equations are this. From equations 1 and 2, you have the expressions for V0 and I0. So, this you can write as V0 by I0 from 1 and 2. The value of Z-in is equal to V0 is V0 plus V0 minus, and I0 is V0 plus by Z0 minus V0 minus by Z0. So, this you can make as Z0 into V0 plus V0 minus by V0 plus minus V0 minus. Okay. Now, thing is, the expression have V0 plus and V0 minus. It doesn't have V0 or I0 as it is, but we need to eliminate V0 plus and V0 minus somehow, so that we can have the expression in terms of Z0, ZL and the known parameters. Okay. So, this can be achieved using equations 9, because we have an expression for V0 plus, and 10 we have an expression for V0 minus. So substituting 9 and 10, let me just name this as equation number 11. 10 in 11, we get Z in is equal to Z0 into V0 plus is given as 1 by 2 Z0 IL e raised to gamma L. So I can write as V0 plus Z0 IL multiplied by e raised to gamma L plus V0 minus is V0 minus Z0 into IL multiplied by e raised to minus gamma L. This is the numerator. Similarly, for the denominator, you have V0 plus Z0 IL e raised to gamma L, which is V0 plus, minus V0 minus Z0 IL e raised to minus gamma L, which is V0 minus. Okay. So, okay, I think there is one mistake I have made, which is this is basically VL, because we are looking at the load, so this is basically VL. V0 is only for the generator side. Fine. Let me take IL from everything out. So this is, so I'll just write it down. Taking IL common from numerator and denominator, we get Z in is equal to Z0 IL into VL by ZL, VL by IL plus Z0 into e raised to gamma L plus IL into VL by IL minus Z0 e raised to minus gamma L whole divided by IL into VL by IL plus Z0 e raised to gamma L minus IL into VL by IL minus Z0 e raised to minus gamma L. So IL is there everywhere, so it will get cancelled. So basically the IL will get cancelled at numerator, denominator, everywhere. And also we have the ratio of voltage and current at the load, which will give you ZL. Okay, so across ZL the voltage was VL and the current through ZL was IL. So if you take the ratio of the voltage and current, it should give you the load impedance. So I can write Z in as Z0 into ZL plus Z0 e raised to gamma L plus ZL minus Z0 e raised to minus gamma L, that is a numerator, divided by ZL plus Z0 e raised to gamma L minus ZL minus Z0 e raised to minus gamma L. That's the denominator. Okay. Now let's expand everything and let's try to simplify this. So this is Z0 ZL e raised to gamma L plus Z0 e raised to gamma L plus ZL e raised to minus gamma L minus Z0 e raised to minus gamma L divided by ZL e raised to gamma L plus Z0 e raised to gamma L minus ZL e raised to minus gamma L. There is a minus here and there is a minus here which will become plus. So we will have plus Z0 e raised to minus gamma. Fine. Let's group all the elements which has a factor e raised to Z0 and group all the elements which has a factor ZL. So basically this has Z0, this has Z0, denominator this has Z0 and this has Z0. Similarly in the numerator this has ZL, this has ZL, in the denominator this has ZL and this has minus ZL. So let's group all the Z0 terms and let's group all the ZL terms. So you will get this is equal to Z0 into ZL multiplied by e raised to gamma L and e raised to minus gamma L. So e raised to gamma L plus e raised to minus gamma L, and there is plus Z0 multiplied by e raised to plus gamma L minus e raised to minus gamma L. So e raised to plus gamma L minus e raised to minus gamma L. That is numerator. At the denominator you have a similar term ZL into e raised to gamma L minus e raised to minus gamma L. E raised to gamma L minus e raised to minus gamma L plus Z0 e raised to plus gamma L plus e raised to minus gamma L. E raised to plus gamma L plus e raised to minus gamma L. Okay. So we have an expression e raised to gamma L plus e raised to minus gamma L is actually 2 cos h gamma L. E raised to gamma L minus e raised to minus gamma L is 2 sin h gamma L. So those are actually cos h and sin h hyperbolic functions. So I can substitute the values here, this and this will be cos 2 cos h gamma L, this is also 2 cos h gamma L, and this and this will be 2 sin h gamma L. This is 2 sin h gamma L. So I can write my Z in as Z0 multiplied by 2 ZL cos h gamma L plus 2 Z0 sin h gamma L divided by 2 ZL sin h gamma L plus 2 Z0 cos h gamma L. Okay, and 2 is common everywhere. So it will get cancelled. So basically the 2 will get cancelled because it is there in numerator and denominator. It will get cancelled. So basically you will finally end up with Zn is equal to Z0 into ZL cos H gamma L plus Z0 sin H gamma L divided by ZL sin H gamma L plus Z0 cos H gamma L. Okay, so this is the expression for your input impedance looking from the generator over a transmission line of length L connected with a load impedance ZL. This is the final expression. You can simplify it further. You can also say this is equal to, you can take cos H gamma L out. So this is Z0 into ZL plus Z0 tan H gamma L by ZL tan H gamma L plus Z0. So this is the final expression. So what are all the terms inside this? Let's look at all the terms. L is equal to the length of transmission line. Z0 is equal to the characteristic impedance. ZL is equal to load impedance, and all others are hyperbolic functions, and gamma is equal to the propagation constant. Okay, so we have found out the input impedance of a transmission line when you look at the transmission line connected to the load at Z equal to 0. Okay, and L is the length of a transmission line. So let me draw the transmission line again. So you have a generator with some input impedance for the generator. There is a transmission line with impedance Z0, and there is a load with impedance ZL. So the transmission line is connected at Z equal to 0 and the load is at Z equal to L, which means the length of the transmission line is L. Okay, so you see there is an L here which comes in your Z in also. So this Z in is from where you are looking at Z equal to 0. So what if you want to find, let's say I want to, if I am looking at this point, what is the Z in here? If you look from here, what is the Z in? Let's say this point is at a distance L from the load. So let's say this distance is L or L dash. So let's say this is Z0. So this is L dash. So this distance is L minus L dash. So what is the input impedance Z in at the point Z equal to L dash, or the point is at a distance L minus L dash from the load. Or you can say in different way. So instead of let's taking as L dash from the generator, let's take it a bit more simpler way. So let's take the point is L dash distance from the load. Okay, it's L dash distance from the load. So it is at a distance of L minus L dash from the generator. So Z in at a distance of L dash from the load, or in other words at a distance L minus L dash from the generator. So what is the value of this term? Okay, so if you want to find the input impedance of the line who is of the transmission line at the point L dash, at the point distance of L dash from the load, what is the input impedance? So this you should submit as an assignment. Prove that the input impedance at a point in a transmission line which is at a distance L dash from the load is given by Z in is equal to Z0 into ZL plus Z0 tan H gamma L dash by Z0 plus ZL tan H gamma L dash. So this is the expression you need to prove. It is exactly the same steps that we have looked up to prove this expression. So whatever steps you have done, it is similar, except that instead of L, wherever you find the value at the load, you need to find at L minus L dash. Okay, so this is the assignment. And submit it by 14/9/2020 before 11:59 p.m. Okay, so that's your assignment, and you can submit the assignment before 14th of September 11:59 p.m. Okay, so this you need to prove. So this lecture we have seen basically the derivation of input impedance at a point, looking at the point Z equal to 0. Basically it is the generator point, and we found that we can derive it by finding the expression for V0 I0, VL IL, and then the Z-in is basically the ratio of current and voltage, voltage and current at the point Z0, and we already found the expression for V0 and I0. You substitute it in the expressions, and then we also found the expression for V0 plus and V0 minus in terms of the voltage and current in the load, and we substitute that also, and then we rearrange everything, and when you rearrange everything, you see that there is an expression in terms of ZL Z0 e raised to plus or minus gamma L. We again rearrange those things, and we found that the expression will come in terms of the hyperbolic functions and ZL and Z0, and then we will finally get an expression for input impedance in terms of hyperbolic functions ZL and Z0 and gamma L. Okay, so this is basically the derivation of input impedance, and you have an assignment to do, and you will and please finish the assignment before the submission date. Okay, thank you.